Today I'd like to demonstrate a unique new VNA from Anritsu, the ShockLine ME7868A distributed two-port VNA. The ME7868A is a two-port VNA consisting of independent MS46131A one-port VNAs controlled from a user-provided PC without the need for a mainframe chassis. This distributed architecture enables flexible placement of the VNA ports near the device under test, or DUT, eliminating the need for cabling or other interconnect between the port and the device. This simplifies test setups and improves measurement stability, which we will see in a moment. With the breakthrough technology from Anritsu called PhaseLync, the two one-port VNAs are synchronized to enable complex two-port S-parameter measurements between them. The technology enables insertion loss measurements with magnitude and phase between the one-port VNAs at distances of 100 meters or more. For this video, we are going to use the 25-meter ME7868A configuration pictured here. It shows the 25-meter PhaseLink cable assembly, the two MS46131A one-port VNAs, two MN25131A multifunction extenders, and a user-provided control PC. The standard configuration also includes USB accessories for operation and communication between the near and far end of the 25-meter setup that will not be used in this video. Here's a block diagram of the setup we are going to use in this video. We have the 25-meter ME7868A two-port VNA set up with two 5-meter cables connecting the one-port VNAs to the DUT. This setup represents the length of RF port cabling that a single chassis VNA might need to interface to a longer distance S-parameter application, like over-the-air testing in a medium-sized chamber or testing larger-sized devices or vehicles. A key advantage of the distributed architecture of the ME7868A is that we can eliminate the interconnect cabling in this type of setup, improving the stability and dynamic range of the measurement. In this demonstration, we are going to compare the difference in phase stability of an insertion loss measurement over distance while introducing movement in the RF port cabling versus the PhaseLink cabling. The movement simulates what the user may experience when setting up multiple measurements in a typical long-distance S-parameter application. Here's the demo setup of the ME7868A. We see here the control laptop showing a normalized insertion loss measurement of the two 5-meter cables connected together with a K-through. Next to the VNA display is a camera view showing a portion of the RF cable and PhaseLink cable assembly that will be moved during the demo to show the difference in phase stability between the two. As we pan to the right, we see the one-port VNA and the 25-meter cable assembly reel, followed by the first of the two multifunction extenders that provides power and USB communications to the one-port VNAs. Continuing to the right, we see the black and yellow PhaseLink cable assembly and the black RF cable in front of the camera that is providing the video we saw on the control computer. Moving further to the right, we see the connection between the two 5-meter cables with a K connector type through. Following that, we see the second MN25131A multifunction extender and the second MS46131A one-port VNA. On screen, we are now showing the two-port S-parameter measurements of the 10-meter cable setup we showed earlier. In the upper right-hand quadrant, we can see the S12 measurement showing the insertion loss of the setup to be about 25 dB at 43.5 GHz. A major advantage of the ME7868A is that we can eliminate that loss and improve the overall dynamic range of the setup by directly connecting to the DUT with portable ports. In the lower left-hand quadrant, we have a normalized S21 measurement. The graph is displaying log mag on the top and phase on the bottom. Let's zoom in on the S21 display. As you can see, the log mag scale is 0.1 dB per division and the phase scale is 2 degrees per division. In over-the-air or RF shielding and propagation testing, multiple setups are typically used to measure at different positions around the DUT. Let's take a look at how movement affects the phase stability of the S21 measurement. To simulate positioning the ME7868A ports for different setups, I'll introduce significant movement on the PhaseLync cable assembly. As you can see, the insertion loss magnitude and phase are very stable, with the phase only changing by less than 2 degrees at 43.5 GHz. Let's compare that to what movement in the RF test port cables would introduce into multiple measurement setups. As you can see, the phase change is about 8 degrees at 43.5 GHz with just minimal cable movement, which is much greater than the change we saw with moving the PhaseLink cable assembly. This illustrates the stability advantage a distributed two-port VNA has over a traditional VNA in phase measurements over distance. The ME7868A two-port VNA is a paradigm-changing solution for over-the-air and other long-distance S-parameter test applications. By combining precise synchronization and excellent measurement stability between portable one-port VNA measurement ports, the ME7868A with PhaseLink technology simplifies and improves long-distance S-parameter testing. For more information, please see the Anritsu website at anritsu.com. Thanks for listening.